tomorrow. This is tomorrow's lab. If you happen to stop by tomorrow, you'll know what we're doing. It's a very simple procedure, but your calculations are going to be a little bit more involved. 100 ml of water. You'll put that into a beaker. And then you need 1 drop of food coloring. Now, does anybody have trouble with drops, like from titrations? Tarun, have your partner do this part. You don't want 2 drops. You want 1. So I have green food coloring up here.
He doesn't even deny it.
Wait.
I'm watching. I'm watching.
Okay. Yeah, don't leave me. Count with me. Ready?
1.
I haven't done anything yet.
2.
1. Good job. That's it. That's all you need. Just 1. Tarun's partner, you are in charge of that. It's not a whole drop. Did anybody see a stream of food coloring coming out? No.
Who's monitoring Tarun?
All right.
I'll take about 50% on this list.
Ellen and Aya and the other girl who I don't know her name. I will admit I lied to you. Waleed did tell me to stall you guys. Do what you got to do. You are thoroughly stalled. Okay, so anyway, you're going to take and swirl your food coloring. So you're going to have a green solution. You're going to add to it some bleach. The bleach is an oxidizing agent. Bleach is the hypochlorite ion, ClO with a -1 charge. What is the oxidation number of the Cl? ClO with a -1. So what is the Cl?
Oh, it's +1.
+2.
So O is a -2, so what's the Cl? +1. How comfortable is chlorine as a +1 oxidation state? Not very. Bleach is pretty reactive as a result of that. The bleach wants to, or the Cl wants to reduce to a -1. So it will be considered an oxidizing agent. Sometimes it'll say that on here, caution, strong oxidizer or whatever. I don't see it on here, but
So you can melt bodies with it?
no, I don't think it's that reactive. You're going to measure out a specific amount of bleach. I think the instructions are going to say use 7 ml. I'm just going to put a splash in there just so you can see what the reaction looks like. As you do this, you're going to mix the bleach into your food coloring and do the next few steps very quickly. You're going to have a spec 20, which is over there in the corner. There will be one at every station. Once you have combined your reactants, watch what happens. It goes quickly. You'll see that there's a color change immediately. It's going to be 7 ml. I'll tell you all this tomorrow. So what is happening is the bleach
drink
is
it, Kyle.
oxidizing the food coloring, and it's causing the food coloring to lose its color. Now, it happens pretty slowly. You can't tell that anything is happening. You just saw immediately the green change to blue. But now, I wanted to do this early enough in the hour. Later on, I'm going to ask you to take a look at this. We're going to see definitely this thing is changing color. The spectrometer would be able to detect that better than our eyes can. So you're going to see the absorbance going down, 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 down as the concentration of it changes.
All right, that's enough.
Nice. You can sing while you're doing your experiment.
I read that as it gets absorbed more, there's more color to show.
Yes. So as the color goes away, the absorbance is going down. That's good. I should ask a question like that. I'm going to take you back to what we did on Tuesday for a moment.
I'm going to get started on
A long
horns.
time ago, we saw first order integrated rate law. Looks like this. I asked you to write this down in your notes on Tuesday and not underline it, but highlight it or box it. Did you do that?
Yeah. Would you like me to start it?
Rasheed, would you care to run the cockpit?
Go
ahead.
I don't have notes though.
You're up.
I don't have the. True, go.
You need it, Tarun.
Tarun.
Here, I'll do
You
it.
don't have to if you don't want to.
I'll do it.
That's fine, I'll do it.
Well,
Kyle, you want it tomorrow? The next day, I guess.
So
One
are
of
they-
these days they're going to replace the circuit.
Yeah, are they gonna fix it?
Yeah, it'll be fixed. Yeah. They ordered something.
Yeah.
There's a circuit board in there that got cooked. The time that we had the power outage, I think it blew up.
That did the trick.
All right. Now listen. I understand. When you look at this, let me get rid of the reading quiz stuff.
Who the heck wrote on my notebook? Probably you.
Yeah, I am going to ask for your cooperation. Eman is nice enough, thank you, Eman, to record this for my first hour students that had to go to the NHS thing this morning. So, yeah, I feel you'll be respectful of those. Thanks. This is the way a rate law looks. I understand we haven't really gotten into what does that order really mean? That exponent term. Remember the K value. I gave you one last slide on Tuesday about the K value. It's called the rate constant, and it's a numerical value that indicates how fast the reaction is going. The exponent tells the order, and really what that does is it indicates how much the concentration of the reactant affects the rate. Now we saw the most common order is first order, and we saw that when you plot natural log of reactions versus time, if it's a first order reaction, it's going to give you a straight line. That means that the concentration of A varies linearly with the rate. If that exponent is not a 1, like sometimes you can have a second order reaction or second order rate. And what that means is the concentration of A is going to affect the rate more profoundly because the concentration is going to be squared this time, and so that's going to affect the rate more than the first order rate. That's all the order means. Now we're going to learn a lot more about order. When we do the differential rate law, and we actually find out how to find this with experimental data, it'll make more sense. But for right now, just know that the order is going to be kind of a fuzzy topic. I mean, we're going to be finding it, and you're going to say, okay, here's the order, but you don't really know what that means yet. You will. There's a lot of things in this chapter that will all come together. It's kind of a long chapter as a result. Huh?
Remind me again, what's the K mean?
K is the rate constant, and that is a number that just tells you how fast the reaction is
Do
going.
we find that out, or do we know it?
You'll have to determine it, yeah.
Oh, okay.
When you find what the order is, then you can find out what K is too. We'll see how to find that too. All right. Tarun, let's go to the next one. And we did this on Tuesday as well. You see that K is called the rate constant. What can you do to speed the reaction up and increase K?
Catalyst.
You can add a catalyst as one thing, yeah? That would increase K. What else?
Increase
Yeah, it
temperature.
says right here, increases with temperature. Heat up a reaction, particles are moving around faster, and they'll react faster. More collisions means more reaction rate, yeah.
Increase volume, pressure.
Yes, squish everything together. Yes, very
Increase
good.
volume.
Right, those are really the same thing. Yep. Okay, so Tarun, let's go to the next one. And we're going to see that, oh, no, I had an example for you. We're going to run out of time, though. Let's jump to the next. I'll have an example for you at the end of the hour, too. Okay, now move that shade back up to just under the bold part. I don't want everybody to see that yet. Okay, so we have another A yields B generic reaction. And this time we're going to find that it was a second order. Again, that's found using an experiment. We'll find out by the end here how to determine that second order. Right now, you just need to be told that's a second order reaction. Second order means, Tarun, give me one more line. Good, okay. That means that that exponent there in the rate law is a 2. That's what second order means. Also remember that the rate is really defined as the change in the concentration of the reactant over time. That's what a rate is. It's how fast something is changing over time. So now if the rate is defined as both of these things, they can be set equal to each other. Now in the interest of just showing you how we get this, I totally get, on Tuesday I know, we did the integration of the first order. I'm going to do that for this one too, just so you see how we get it. Remember, you're not asked ever to derive this or do any integration yourself. So if you hadn't learned how to do integration, then you're not going to freak out, okay? So what we have is we have this relationship. I'm going to leave the rate out and just set this term equal to that term. And I'm going to change the deltas to D's. Remember what D is? D is like a very small change in some interval.
Oh.
All right, so we're going to have this. K times concentration A squared, remember it's second order, so it was a 2 coefficient, or a 2 exponent, equals negative D concentration of A over dt for time. What I'm going to do is take and put the A terms all on one side. So right now I got an A term there and an A term there. I'm going to move them to one side, and then I'll bring the dt over here. That's called a differential equation. Does that make your stomach upset, Jessica?
It's not that bad.
All right, so I need to move the A squared over to the other side. So the other side, the A side is going to look like this. 1 over A squared times dA. Is that okay if I write it like this? I could have put dA over D or A squared, but I wanted to do it like that.
Okay.
I'm going to move it over to the other side. Now the dt came over here with the k, so it's k dt, negative k dt. I just did the other. Really, it should be written k dt equals 1 over A squared dA over on that side, but I just took that thing into it. This is correct, yeah?
Yeah.
Okay. And we do have that negative term in there. Okay. Now, if we integrate both sides over some time interval t, calculus wizards, what is the integral of 1 over A squared? No, that's just 1 over A integrated.
Yeah, negative 1 over.
Yes, negative just 1 over A.
I knew that. Negative 1 over A.
Okay,
Dude, yeah.
so all right, that's fine. You haven't done this kind of integration yet?
I haven't done it. Yeah, I did.
Yeah.
Okay, so here's the way it looks. 1 over concentration of A at some time t, I'm sorry, it's negative, it is negative, minus negative 1 over concentration of A at some time 0 equals, this side integrating it over some time interval t is going to be kt minus 0, so it's just negative kt. And so rearranging this thing, solving it for 1 over concentration of A, Tarun, let's just bring that whole thing down. All right, integrating. I have taken this. See all those negatives in there? It turns out that when you solve this thing for 1 over A, everything turns out to be positive. Well, everything really turns out to be negative. Then you just divide through by negative 1 or multiply through by negative 1. And that gives you all positive values. So, if you have a second order relationship, you have 1 over the concentration of A is equal to K, that rate constant, times time, plus 1 over the initial concentration. Looking at this thing, K is a constant value. K for constant, right? 1 over A0. This is also a constant because this is the inverse of the initial concentration. That doesn't change. Whatever the initial concentration is what it is. And even though the concentration changes, the initial concentration doesn't. What it was at the beginning doesn't change. So we have a variable equals constant times a variable plus a constant. Is this also the equation for a line, straight line?
Yeah.
Yes.
Yeah.
It's the equation for a line. So this is another highlighter statement. Second order reaction means that if you plot the inverse of the concentration versus time, that will give you a straight line. Are you making that stand out in your notes? That's big. It's huge. Let's take a look.
So first order, it's just a direct relation.
No, it's natural log of the concentration versus time in a straight line.
Yeah. First order.
First order is natural log of the concentration versus time. It's a straight line. Didn't you write that down?
No,
Let me see.
I did not.
I told you to write it down and highlight it.
Oh,
Oh, it's right there.
What?
Oh, but then you didn't write. This part in red, that's important.
All right.
Take a look at this.
So by looking at a graph, you wouldn't be able to tell whether something is first order or second order.
You would or wouldn't?
I'm asking would you be?
You would, yes. Yeah.
Wouldn't they both be straight lines?
No, only one will be a straight line. If it's a first order relationship, then the natural log of the concentration of the reactants versus time is going to be a straight line. The inverse of the concentration versus time will not be a straight line. It'll be a curved line.
Oh,
So yeah, only one of those will give you a straight line, and that tells you what order it is.
okay.
So yeah, remember our food coloring? This is it. So you see how the concentration is changing of food coloring. Yeah? There it is. And that will continue to change, not by much, but it'll get a little bit lighter, I think, over time. You're only monitoring in the lab tomorrow for like 3 minutes. Yeah? It won't absorb as much light.
What? What's A?
Right, it won't. Yes, it won't
A
absorb.
is
The darker it is, the
reactant.
more absorption. Yep.
Wait, A is some reactant, right?
Yeah, A is the concentration of the reactant. Yep. This is how you tell if a reaction is first order or second order. You take what the concentration is versus time, and you have to plot the natural log of the concentration versus time. If that gives you a straight line, that means it was first order. If you plot that and you don't get a straight line, then you try inverse of the reactant concentration versus time. If that gives you a straight line, that means it was second order.
Oh, so that's how we find K.
Yes. And then yeah, for K, you can just take any data point and plug in the concentration there and the time, and that'll give you K.
What if it's still not a straight line? Would it go to Would it go to third order?
I don't really know how they start flying this thing.
If it's not, what if it's not first order and it's not second order? Then you have one other choice, and that would be zero order. I think there are third order reactions out there, but I have never seen one. I don't know what it looks like, and I don't even know the integrated rate law for it. I mean, we can figure it out if I remembered any calculus, but I don't.
Okay, I'm watching you.
What it would be? It would be -2 over a squared.
It's up to you.
But yeah, don't worry about it.
Yeah.
Terrell, let's go to the next one.
Because it was on sale. I guess I'll take for like $100.
All right. Now let's take a look. You can also have a zero order integrated rate law. So we have first order and second order. The only other choice is a zero order. And zero order means, let's go down just a little bit. Okay, that means that the rate is equal to K times A to the 0 power. What does that tell you about the relationship of the concentration and the rate? Does the concentration affect the rate?
No.
Raised to 0 power? No. What would a graph look like for this thing? The rate would just be constant no matter what the concentration of A was.
Horizontal.
Yeah, just a flat straight line. Yep. So that would be equal to the change in A over T. Tarun, let's just drop the rest of that. Now, if we were to combine the similar terms, make a differential equation, and integrate both, we would get this relationship for zero order. Just the straight up concentration versus time gives a straight line if it's zero order.
Wait, if it's the power 0, would that make it 1?
Yes, that means just
Yeah.
rate equals K.
Still a straight line.
Oh, so
Yeah.
yeah, that makes sense.
So write this down, it's written in red, highlight that. We have second order, first order, zero order. That's how we know what order the reaction is. Later on you're going to find out what the order really means to us.
Is it important?
Yeah. We can learn a lot about the way a reaction is proceeding by knowing what the order of the rate is. So.
Do you have any extra notebooks I can have? This one's like.
Finally,
Look
not
at this.
your mother. Buy a notebook.
Spencer will get one for you tomorrow.
I absolutely will not. Take it for the office.
He'll let you borrow his iPad, then you don't need any paper anymore.
Never.
Spencer will
Who
go with
would
that.
take some notes on an iPad? Who would do that?
All right, everybody go with that slide?
Yeah.
What kind of
Oh.
cruel teacher would make people take notes on an iPad?
Let's flip the page.
Push
Nice off.
What's with the gap over there? I don't get this. What gap?
Revenge for what?
For all
What?
this time that you threw carrots at me.
Where's the
Carrots at you?
And put random things in my hood.
Oh, this is
I
I guess it's kind of your fault for wearing a jacket every single
Okay,
Yes,
you
it's
spilled
my
milk
fault
on
for
my
wearing
lunch.
a jacket.
Who is just like milk laying
all
around?
recorded,
Take it out on
guys?
someone else, okay?
What is that?
Jessica's just like a
Take a look at this problem. Number 39. This is one of the assigned problems in the book for this chapter. Butadiene.
Ooh. It sounds fancy.
Now you know what butene is, right? Butene means it's got a double bond in it. Ene. Well, butadiene means that there's two double bonds in it. Diene. It's diene.
Totally forgot about this.
And dimerization is kind of like polymerization. When you have a dimer, that just means you've got a monomer that has attached, two molecules of it have attached, and it has made just two repeating units, a dimer. And if you have three monomers stuck together, that's a trimer, like that. And after that, it's a huff. Okay, so that reaction was studied, and what are we given here? We're given time versus concentration. So the question is, determine the form of the rate law, comma, the integrated rate law, and the value of the rate constant K. So yeah, you were asking earlier, do we always have to find K? You always have to find K. Yep. So how would we find what the rate law is? How do we know what the order is? Well, we start plotting. This is why I asked you about your calculators earlier. You grab your calculator and you're going to plot. Now don't do it. We don't have time for it. I have already graphed them and we're going to take a look. You would plot the concentration versus time. And if that's a straight line, then you're done. It's zero order. You write down in zero order, you write your rate law, and you're done. But if it's not a straight line, then you've got to take the natural log of these values and then plot again.
Wait, natural log
Of the concentration
versus time.
versus time. If that's a straight line, then you know there's a first order. So you write your rate law and you're done. If that's not a straight line, then you take the inverse of these values and you plot them versus time.
Oh wait, there's an easier way to do this.
Kyle?
There. Could you just like plot all these and then recognize if it's a natural log graph or an inverse graph?
No.
All right. I don't know. Maybe I've forgotten too much math. Tarun. Oh.
Quick question.
Yeah?
Would you, the concentration values, those are the X values, correct?
Well, a natural log
And then the Y value are the time?
No, time is always on the X. The X is independent variable. Time is always independent. Tarun, there's a paper clip. Would you click on it?
like this.
Yeah, it's something like that.
The inverse is like.
All right, take a look. Gang, we are going to have laptops in here tomorrow. It would really be nice if you could make an Excel graph. Do you know how to make Excel graphs? Scatter plot? You're going to have to turn in a printout of graph as part of your lab write-up. All right, Tarun, I want you to click on that top graph and make it much bigger. So, hey, before you do that, Tarun, take a look at what I've done here. I have the time. I've got 5 data points. Time versus concentration. I plotted that graph. Go ahead and expand that. No, grab that bottom corner, yeah, and make that nice and big. Bigger. Nice.
Not big enough.
All right, Kyle, this is the question that you had. Oh, now, don't worry about, well, all right, go ahead. Nice. Okay, so this we have, this is just straight up concentration versus time. Is that a straight line?
No.
No. Now, can you tell what the order is from looking at that?
No.
I can't.
I think it's second.
I can't.
Okay.
So, we know for sure, though, it's not first, I'm sorry. We know it's not zero order because the plot of concentration versus time is not a straight line. Tarun, make it small. And then let's go to the natural log graph.
Wait, is that second order?
Yeah.
Well, hold on. Let's see.
Look like a pretty straight line to me.
Okay, this would be, is this first order? Natural log of the concentration versus time. Straight or no?
No.
Somewhat, not
It
yet.
has to be perfect.
Get in there.
We want the closest possible straight line. This is pretty close.
I think that one's hard.
You're going for that one. All right, let's take a look at that. Let's expand that.
We figured out straight line.
Ha! I was right.
I was right.
Yeah.
Now, do you believe that is straighter than the one you just saw?
Yeah.
What about if you're not sure? Well, what you can do,
Eccentricity.
okay, now unfortunately, you can't read the top of the,
Yeah, you can do this.
what happened to
Wait,
our
what do you think about that?
ribbon? Okay.
Log graph is something like something.
I want you to take a look up here.
Oh,
Click on
wait.
one of the graphs.
You can look
Click
at
on
the
this big
R-squared
graph.
values.
Okay, now listen to this. You see you got chart tools up here. Click on layout in the middle of the chart tools. And go over to the right to trend line. To the right. Okay, now go all the way down to more trendline options. This is so good. The very bottom, so display R squared value. You know what the R squared value is?
Yes.
The R, yes, you've done it if you have physics. It tells you how close a set of data is to linear. And go ahead and close. It gives you, it's fine print up here. The closer R squared is to the value of 1, the more linear your data is. This is an R squared value of 0.9995. I like this. Yep. So I think Eric had it at the very
It's
beginning.
not quite an A+ yet. Dude.
Now, if we would have plotted the natural log data, that gives an R value of around 0.98. So it's still pretty linear. But this one is definitely the more linear of the two. So if you're not sure, if you want to make that R squared value, that's handy.
I don't think I can add trend lines on my code.
This is what we're going to do on our lab tomorrow. You're going to monitor the absorbance of light of your sample over time. It's about over 3 minutes. And you're going to have concentration versus time data.
How would we find the concept?
Mr. Moore,
Oh, from your plot. I'll give you a plot.
Mr. Moore, the shortcut works.
What's that?
The shortcut works.
What
I
shortcut?
would love to do that on
So you
this.
plot
Like, okay,
concentration versus.
Wait, time out. Rashid has a shortcut he wants to share with us.
Well, Kyle came up with it. But
Thanks.
Always take credit.
well, you plot the concentration versus time, and if it's like a inverse graph, which is like this, then it's the second order.
Then a second order, okay.
And if it's like this, then it's
It's got to have, the concentration versus time got to have a negative slope, so it's going to go like that
yeah.
from ln.
And then
I'll check that.
should I put that on the TI before?
If you have the option to balance.
Yeah, I'm not sure either, but anyway, yeah, maybe so.
like this.
All right, anyway, that's what we have in the lab tomorrow. Hey, man, thank you for